Atomic number and mass number. Let us learn about the atomic number. From the alpha scattering experiment, Rutherford and his associates established the presence of positive charge in the nucleus of an atom due to protons, and estimated the number of positively charged nucleus of the atoms on the metal foil. They used different metal foils and found the number of positive charges present in each case. Rutherford was the first to establish in 1919 the independent existence of particles called protons, which are the fundamental unit of one positive charge. He found the existence of protons by the studies carried out on the passage of alpha particles in hydrogen. Henry Moseley, under the guidance of Rutherford, tried to determine the exact number of positive charges present in the nucleus of an atom. He stated that the number of unit of positive charges present in the nucleus of an atom is known as the atomic number of the element. It is denoted by the symbol Z. We know that all the protons are present in the nucleus of an atom and each proton has a unit positive charge. Therefore, the atomic number of an element is the same as the number of protons. In an atom, protons and electrons are the same in number since the atom is electrically neutral. Therefore, the atomic number of an element must also be equal to the number of electrons. Thus, atomic number is equal to number of protons, which is equal to number of electrons. We have already learned that protons and electrons are constituents of atoms. But on taking into account the protons and electrons, all the mass of atoms cannot be accounted for. Let us take an example. Atomic mass of hydrogen is 1. Its nucleus contains 1 proton. But the atomic mass of all other elements cannot be correlated to number of protons in the nucleus. Let us take an example. Atomic mass of helium is 4. An atom of helium has 2 protons and 2 electrons. As charge is balanced, therefore an atom of helium as a whole is neutral. Because mass of 2 electrons is negligible, therefore mass of helium should be 2 due to the presence of 2 protons, each having a mass equal to 1 atomic mass unit. In order to account for the remaining mass, existence of a neutral particle having mass almost equal to that of a proton was proposed. Presence of 2 neutral particles in the helium atom can make the mass of helium equal to 4. James Chadwick was successful in discovering the neutral particle, neutron, inside the nucleus. Let us see how he did it. Let us now learn about discovery of neutrons. When James Chadwick bombarded a thin sheet of beryllium element with alpha particles, then he observed the highly penetrating rays which consisted streams of neutral particles. Each neutral particle present in the obtained rays was having no charge but was having a mass of 1.67 into 10 to the power minus 27 grams, which was nearly equal to that of a hydrogen atom. The new particles formed were given the name of neutron and denoted by the symbol N. Thus, neutron may be defined as a fundamental particle present in the nucleus of an atom which carries a mass of 1.67 into 10 to the power minus 27 kilogram, regarded as 1 unit mass and no charge. We have studied the 3 subatomic particles that is electrons, protons and neutrons. Out of these, protons and neutrons are present in the nucleus, while electron is present in the extranuclear portion. We can sum up this information as follows. Proton, symbol P+, with a mass of 1.67 into 10 to the power minus 27 kilograms and a charge which is equal to 1.67 into 10 to the power minus 19 coulombs. Electron is E minus with a mass which is equal to 9.1 into 10 to the power minus 31 kilograms, which is negligible, and a charge of 1.67 into 10 to the power minus 19 coulombs. Neutron is denoted by the symbol N with a mass of 1.67 into 10 to the power minus 27 kilograms and no charge. Remember that electrons, protons and neutrons do not have any identity as such. Atom is still the smallest particle of matter which is involved in chemical combination with other atoms. Protons and neutrons present in the nucleus of an atom are also called nucleons. Let us now learn about the mass number. The discovery of neutrons by Chadwick made it quite clear that the nucleus of an element has protons and neutrons, as well as an explanation of emission of negatively charged beta particles from nucleus and also the mass of an atom. The original prediction by Rutherford proved to be correct. Since each proton and neutron has mass equal to one atomic mass unit, therefore, mass of an atom must be the same as the sum of protons and neutrons present in the nucleus. The latter is known as a mass number of an element. It is denoted by the symbol A. The mass number of an element may be defined as the sum of the number of protons and neutrons present in the nucleus of its atom. Let us now learn about composition of atom. From our discussion so far, we conclude that an atom is electrically neutral, that is, it has no charge. In an atom, protons and neutrons are present in the nucleus and electrons in the extranuclear portion. Atomic number of an element is equal to number of protons in the nucleus. Mass number is the sum of protons and neutrons present in the nucleus. Atomic number is equal to number of protons. Mass number is equal to number of protons plus number of neutrons. That is, atomic number plus number of neutrons. For example, the mass number of the element aluminium is 27 and its atomic number is 13. Therefore, number of protons is equal to atomic number, which is equal to 13. Number of electrons is equal to number of protons, which is equal to 13. Number of neutrons is equal to mass number minus atomic number. That is, 27 minus 13, which is equal to 14. When an atom loses an electron, it forms positive ions. But there is no change in the number of protons. There is no change in the nucleus. For example, sodium with atomic number 11 forms Na plus ion after losing one electron, but its atomic number is still 11. The number of electrons in sodium ion is one less than the electrons present in neutral sodium atom. We will now learn about the representation of an atom. The atom of an element is generally represented by the symbol of that element. The atomic number is indicated on its lower left side of its symbol, say Z, and the mass number on its upper left-hand side. The mass numbers and atomic numbers of some elements may be shown as represented on the screen. Let us now discuss an example. There are 15 protons and 16 neutrons in the nucleus of an element. Calculate its atomic number and mass number. How will you represent the element? And now the solution. Atomic number of the element is equal to number of protons, which is equal to 15. Mass number of the element is equal to number of protons plus number of neutrons, which is equal to 15 plus 16, that is 31. Representation of the element is 31x15. The element with atomic number Z equals 15 is actually phosphorus. It is represented as 31p15. Let us take one more example. The symbol of oxygen atom is 16O8. What is the name given to the number of protons in the nucleus of the atom? Solution. Number of protons in the nucleus of the atom is known as its atomic number. Atomic number of oxygen is equal to 8. What is the name given to the number of protons plus number of neutrons in the nucleus of the atom? Solution. Number of protons in the nucleus plus number of neutrons in the nucleus is known as its mass number. Mass number of oxygen is equal to 8 plus 8, that is 16. For each atom, determine the number of neutrons in the nucleus and give the number of electrons present outside the nucleus. Solution. Atomic number of fluorine is 9. Number of neutrons is equal to 19 minus 9, that is 10. Number of electrons is equal to 9. Atomic number of iron is equal to 26. Number of neutrons is equal to 56 minus 26, that is 30. Number of electrons is equal to 26. Atomic number of copper is equal to 29. Number of neutrons is equal to 64 minus 29, that is equal to 35. Number of electrons is equal to 29. Isotopes are atoms of the same element which have the same number of protons but different numbers of neutrons. Therefore, isotopes of the same element have the same proton number but different neutron numbers. The name isotope is derived from the Greek word isos, meaning equal, and topos, meaning place. This refers to the fact that all isotopes of a particular element have the same position in the periodic table. Most elements have more than one isotope. To differentiate isotopes of the same elements, their neutron numbers are written after their names. For example, a carbon atom can occur naturally in three forms, namely carbon-12, carbon-13 and carbon-14. These carbon atoms have the same number of protons but different number of neutrons. These carbon atoms are called isotopes. Let us have a look at all the isotopes of hydrogen at a time. The simplest element, hydrogen, has 3 isotopes. Because of their importance, they have been given their own name and importance. Hydrogen-1 is referred to as protium. Protium has an atomic number 1 and mass number 1. This means that it has 1 proton, 1 electron and no neutron. The isotope hydrogen-2 is named as deuterium and is designated by symbol D. Natural hydrogen contains 1 deuterium atom for every 6,666 atoms of protium. Deuterium isotope of hydrogen has 1 neutron besides the proton. This means that its atomic number is 1 and mass number is 2. Because of the fact that deuterium is twice as heavy as protium, it is called as heavy hydrogen. Water containing deuterium is referred to as heavy water. 100 cubic centimeters of water has a mass of 110 grams. Hydrogen-3 isotope of hydrogen is referred to as tritium and is designated by symbol T. Natural hydrogen contains 1 tritium atom for every 10 to the power 16 protium atoms. The tritium nucleus is the heaviest of all hydrogen isotopes as it is made up of 1 proton and 2 neutrons and has atomic number of 1 and mass number of 3. Tritium is a radioactive isotope and it emits beta particles. Oxygen-17 has 8 protons, 8 electrons and 9 neutrons. Oxygen-18 has 8 protons, 8 electrons and 10 neutrons. Uranium-235 has 92 protons, 92 electrons and 143 neutrons. Its mass number is 235. Uranium-238 has 92 protons, 92 electrons and 146 neutrons. Its mass number is 146. Isotopes of the same element have same proton number. Hence, they share the same chemical properties. They have different masses and can be shown with the help of an experiment. Let us take a beam balance and place an atom of chlorine-35 at one end and an atom of hydrogen at the other end. Since hydrogen is equal to 1 atomic mass unit of 1 unified mass represented as U, we find that in order to balance the beam, 35 hydrogen atoms are needed. Mass of chlorine-35 isotope is 35 AMU. If we take a heavier chlorine-37 isotope, we find that 2 more atoms of hydrogen are to be added to balance the beam. So, the mass now is 37 AMU or 37U. Let us now learn about the applications of isotopes in our daily life. There are 2 types of isotopes: radioactive and non-radioactive isotopes. There are about 2700 isotopes of various elements. All of them are not stable. Let us take an example. Natural carbon is a mixture of 3 isotopes, 2 of which are stable and the third one, carbon-14, is unstable. Nuclei of an unstable isotope undergoes spontaneous change over a period of time. The unstable carbon isotope, carbon-14, emits radiation and changes its nature as a result of neutron changing into a proton. So, it turns into a different element, nitrogen-14. Unstable isotopes which undergo disintegration like this with the emission of radiation are referred to as radioactive. Radioactive isotopes produce harmful radiation. They can have important uses if handled properly. They can be used in medicine, industry, agriculture, archaeology, and the like. Medicinal uses. Gamma rays emitted from cobalt-60 are used in radiotherapy for treatment of cancer. A heart pacemaker which contains plutonium-238 is used to regulate the heartbeat of patients with heart problems. Iodine-131 is used in the treatment of thyroid diseases. For example, the radioisotope iodine-131 is used to diagnose problems in the thyroid gland. The thyroid gland normally absorbs all isotopes of iodine. Therefore, a PET scan on a healthy patient would show the injected iodine-131 to be absorbed by it. However, if the thyroid gland is not functioning properly, the iodine-131 will not appear to be absorbed, showing a cold spot on the imagery. Let us now learn about agricultural applications. The uptake of phosphate and the metabolism of phosphorus by plants can be studied using a phosphate fertilizer containing phosphorus 32. Food irradiation is a method of treating food in order to make it safer to eat and have a longer shelf life. This process is not very different from other treatments such as pesticide application, canning, freezing, and drying. The end result is that the growth of disease-causing microorganisms or those that cause spoilage are slowed or are eliminated altogether. This makes food safer and also keeps it fresh longer. Food irradiated by exposing it to gamma rays of a radioisotope, one that is widely used is cobalt-60. The energy from the gamma ray passing through the food is enough to destroy many disease-causing bacteria as well as those that cause food to spoil, but is not strong enough to change the quality, flavor or texture of the food. It is important to keep in mind that the food never comes in contact with the radioisotopes and is never at risk of becoming radioactive. Radioactive tracer studies using carbon-14 have helped in the understanding of photosynthesis and protein synthesis. We will now learn about the archaeological uses. Carbon-14 can be used to estimate the age of bone, wood or fossil by measuring the fraction of carbon-14 it contains. Our atmosphere is constantly being bombarded by a stream of energetic particles called cosmic rays. When a cosmic neutron hits the nucleus of nitrogen, the main component of the atmosphere, it transforms into the radioactive carbon isotope C14. This isotope in turn decays, emitting beta radiations with a half-life time of 5,730 years. The balance between the rate at which an isotope is generated by cosmic rays and the rays at which it disappears by radioactive decay maintains the concentration of C14 in the atmosphere at a constant level. The isotope in the form of carbon dioxide is absorbed by plants and indirectly by animals. Therefore, it is assumed that the concentration of C14 isotope in all living organisms is the same as in the atmosphere. When the organism dies, it ceases to exchange carbon with the surroundings. The level of C14 falls gradually as the radioisotope decays. Measuring the amount of C14 in archaeological and paleontological findings allows an estimation of the time when a particular organism died. Industry. Sodium-24 can be used to trace leaks in gas or pipes and ventilating systems. How many of us have smoke detectors in our house? Chances are that a great number of homes have had one or more of these devices installed as an early warning system in case of fire. What most consumers don't know is that many of these units contain a small amount of americium-241. By utilizing the radioactive properties of this material, smoke from a fire can be detected at a very early stage. This early warning capability has saved many lives. In fact, studies have shown that 80% of fire injuries and 80% of fire fatalities occur in homes without smoke detectors.